eat food.
All right, folks. So let's take a look at the question here today. When you're driving in a car, or you're just a passenger in a car, sometimes you have to brake. And when you brake, your body seems to lunge forward. Why is that? Inertia, yes? Momentum. You guys aren't wrong, and those are all those are right words. I'm looking more of a kind of a real world way to describe why it is. Yes.
You're a loose object, and the car's pointing its energy like that. It's using up into the brakes and wheels, but you just your energy just keeps moving forward.
Okay. So it have something to do with energy, maybe. Chip. Inertia, that's true. So the reason that your body feels like it's lunging forward when you brake is simply because yes. Oh, yes.
Is that why when I hit my garage this morning I flung forward?
Yes. The reason that your body flung forward when you hit your garage, are you okay? Okay. Is because when you're moving, your body wants to keep moving at that same speed forever. Just like when you're sitting still, your body wants to keep sitting still forever. But if someone comes up from behind you and gives you a good shove, you feel that. And you feel that as kind of a jerking force. And the reason for that, keep it down a little bit, guys, is because your body wants to stay at rest if you're already at rest. And if your body is already in motion, it wants to just stay in motion. And we have a law for this. This is called Newton's first law. So just quick to answer the question, you would say just something like your body wants to just keep moving. Your body wants to keep moving. It doesn't want to slow down like the car does.
You ever thought about how weird tasting is?
No,
The sense of taste?
I have not thought of that. Have you?
I just did.
I guess so. So, like I mentioned, in terms of you feeling these forces, when you're holding still, you naturally just want to stay still. If you're in motion, you want to naturally stay in motion. And Newton has a law for that. It's called Newton's first law. Newton's first law of motion says that an object in motion wants to stay in motion. And an object at rest wants to stay at rest. And that's going to be the foundation for a lot of the things that we talk about in this chapter, which, as you guys pretty much unanimously said as an answer to the question, is inertia. And in order to describe just quickly inertia, inertia is basically how difficult it is for an object to either get moving or how difficult it is for an object to stop moving. You know, the inertia of a bowling ball in motion is much greater than the inertia of a baseball in motion. It takes a lot less work to slow down that baseball than it does that bowling ball. So that's what inertia is. And in order to kind of understand where this is all coming from, we have to have a little bit of an understanding of history. As I mentioned yesterday, I do like history, and the history of science is rather fascinating to me. The way that they used to describe force and motion and why things move the way they do has changed dramatically over the years. Have you guys heard of Aristotle?
Yeah.
All right. So he was around, anybody know, like 3,000 years ago or something? Something like that.
6 billion years ago.
He was around before Christ, quite a long time before him. But Aristotle had this idea that, you guys have heard of like the 4 elements, right?
3.
Earth, air, wind, and fire. Aristotle believed that these 4 things had their own natural place in the world. That earth was the lowest, and above earth you had water. That's where its natural place was. And air's natural place was above water. And fire's natural place was above the air. And he believed that the reason things move the way they do is because these objects are just naturally trying to find their natural place. He'd say that, when you drop a rock in water, it goes down in the water because Earth's natural place is below the water. And he'd say that when you blow bubbles in water, they go up, they ascend, because air's natural place is above water. And he'd say that fire, its natural place is above the sky, and when you light something on fire, the flames seem to try and ascend higher and higher. And he said that happens because fire's natural place is above the air. And so you can kind of see how, this sort of makes sense. In the end, though, when people started to do real legit science and tried to quantify these things in terms of numbers, his theory broke down in a lot of different ways.
What about boats?
What about what?
Boats. Would those be like air, or would they be...
That would be air, because you've got air inside the boat, and that's the reason it would float, he'd say. So in the medieval times, from about 800 until 1500, they had different ways of describing force and motion. They ditched Aristotle and the Aristotelian view, and they believed in a couple other different things. Basically, the medieval idea was something known as impetus, and what they thought was that when you throw something, you impart a force to it, and over time that force decreases and eventually goes away. If you had bowling back in the medieval times, they would say that when you let go of that bowling ball, you have a force on it, and that force over time gets smaller and smaller. They'd say if this is your bowling ball right here, right when you let it go, it has a force in this direction, and eventually it slows down. And as it's slowing down, that force is decreasing and decreasing and decreasing, and eventually, when it slows down completely and it comes to rest, there's no force at all acting on it. That's the medieval way of looking at things. They'd say, if I throw my Newton's apple in the air, that when it leaves my hand, it's a Newton's apple. And what I usually do is I throw it around so you can feel how heavy it is, because we don't deal with pounds in this class, we deal with newtons, because we got to do correct SI units. And I would do that, but I suppose I probably shouldn't because of the pandemic and everything. So at some point, feel free to feel how heavy this is. This is 1 Newton right here. So if I threw this upwards, the medieval way of doing science would say that as soon as it leaves my hand, it has a force upwards, and as it goes higher and higher and it slows down and it slows down, that force decreases, eventually reaching nothing. And then when it turns back around, things change. Now,
Is it heavier or lighter than real?
it feels lighter. Say it's lighter. I actually have a real apple in my lunch today. I suppose I could compare. Yes. Sure. Make sure to wash the pass when you get back. So, in terms of how we look at things now, we no longer look at things from a Newtonian perspective. We look at things from a Newtonian perspective. So instead of looking at things in the medieval way, we've kind of advanced a little bit. Newton came around in about the 1600s, and he had a different way of looking at things. Newton would say that as soon as you let that bowling ball go, you don't have any force left over from your hand on it. Because he'd say that, imagine there's no friction in the world, and you slide something on the ground, or you roll that bowling ball. Newton would say it's going to continue forever, in a straight line, without slowing down, because an object in motion will naturally stay in motion, unless you have a separate force acting on it. Of course, in the real world, what would that separate force be? Friction, yeah. So when you've got friction there, he'd say that's why it slows down. It's a separate force. It's not because the force you gave it is decreasing. It's slowing down because there's a separate force making it do that. And he'd say that when you throw something in the air, there's no forces on it, aside from a couple things that we'll talk about when we get into these force diagrams here. So Newton basically eliminated that force that you supposedly impart on something that remains with it. As soon as something leaves your hands, Newton would say that whatever force you gave, it's no longer acting whatsoever. So, to kind of think of this, imagine you've got a baseball out in space, and you throw it. That baseball is going to continue forever in a straight line.
Unless it hits something.
Unless it hits something like an asteroid or the gravity from a planet takes it over. but there is really no air resistance in space, so that baseball would just continue forever in a straight line because of Newton's first law. An object in motion naturally stays in motion, and there's no separate force like friction out there. It's just going to keep on going and going and going. And imagine one way you can minimize the effect of friction is by having air pucks. That's a way that you can kind of minimize the effect of friction. And this object would keep going and going and going until it pretty much hits something. You know, move your backpack just a little bit that way. So when there's very little air resistance, it's just going to keep on and going. And that's because, as Newton's first law says, an object in motion is naturally just going to stay in motion as long as there's nothing out there to stop it from moving. But even with this little air puck, there's a small amount of resistance. Even if there's no resistance between the ground and this, you've got air resistance acting. So there's always some sort of friction that's going to mess up your party, unfortunately. Now, in addition to this, it's not just about things that are moving where we have different forces. Let's say we get our apple back out. It is at rest on the table. We deal with a lot of force diagrams in this class. Can you tell me, suppose I should use red. Can you tell me what forces you believe are acting on this little apple as it sits on the table? See how much you can remember from physical science. I heard gravity. And the way we label gravity in this class, and you don't have to take notes today. We're going to have official notes on this tomorrow. Sorry. The way we call the force of gravity in this class is F with a little g, force of gravity. One way that you can start all your force questions in this chapter and any other chapter in physics is by throwing in this force right away, because it's always going to be there. So as long as you start with gravity, you know that you didn't start wrong yet.
Isn't that like 16T or something?
Yeah, that's what it boils down to when your force of gravity is mass times 9.8. So what else is acting on the little apple?
Applied force.
An applied force? What direction? An applied force maybe this way? Okay. No, it's just at rest right here.
I don't know.
Okay, so there's an upward force. What do we call that one? We call this the normal force. So we label it Fn. Now, we've got most of these forces here. Gravity down, normal force up. Gravity is pulling it down like it's pulling you and me down. And, just like you and me are not accelerating down through the floor into the foods room right now, this apple is not accelerating down either. If gravity was the only thing acting, that's exactly what it would be doing. But this normal force is preventing that. Just like the normal force on your butts right now are keeping you from falling to the floor. So wherever you've got gravity down, unless you're in free fall skydiving, you've also got another force going up. We call that the normal force. Applied force is something that we would have if I was pushing this apple across the table. Applied force is a force of push. Any guesses on what we call something if instead of pushing, we pull? Yes. Yes.
The neutral force, neutral or whatever. Is it? What is the answer?
That's the normal force.
Normal, sorry.
Yes.
The normal force, does that only happen when there's something under you? Like you said with free falling?
Yeah, if there's something preventing you from falling down to the middle of the earth, then you're going to have this normal force here.
So like if you got rid of that, I don't know, like table or island or whatever, that apple would fall. So with the webcam and everything under it.
Yep. Because then you just have gravity. And if gravity is the only thing acting, then everything's going to be going down. So in terms of what we call a force if we're pulling, we call that Ft. Any guesses on what the T stands for?
True force.
Nope. I had a good guess last hour. They said tug force. That's a really good guess. We call it the tension force, though. So if you're pushing something, it's an applied force. If you're pulling something, it is a tension force. So, just a little bit more practice with some of these force diagrams here. Because I really want to make sure that not only can you actually do these force diagrams, but you have to make sure you can connect them with Newton's laws. It's a combination of those two things that's going to make you successful in this chapter. Alright. So I'm in the back of the room right now, and I want you to consider what forces are acting on Mr. Hathaway after I let go of the table. What's acting on Mr. Hathaway right now?
Gravity.
Applied force.
Applied force.
I heard gravity, I heard applied force.
And normal.
And
anything else?
Normal.
Normal force.
Friction.
Friction. Very good. So those four things, we've got applied force, normal force, friction, and gravity. Now, what was acting on me after I let go of the table? You named four forces. Of those four forces, we want to make sure that we're aware of what was acting on me after I let go of that table. Once I finished pushing off. You guys mentioned gravity. You mentioned normal force. Once I let go of the table, what's going on horizontally? I heard applied.
Yeah. Wouldn't it still be friction?
And friction. Okay? Okay. So, here's the thing. I'm going to be reiterating this a lot because it's very important. Once I let go of that table, there's no force from that table left over on me. Unless I'm actually touching it, that force is gone. So as soon as I let go of that table, my applied force is history. And the only thing acting on me is friction. Now this is kind of, and of course if the problem said, friction is negligible, that means you can ignore it. In that case, friction would be gone too. So let's ignore friction for now. We'll throw it in just a second. I want to make sure we have this down. How is it possible that I can be moving to the right when there's nothing acting on me horizontally? Michael.
So would force just be pretty much like you put a certain amount of force in, now you're pressed just to get up to a certain velocity. Now you're just going along, so it's kind of like the acceleration, but once you reach that, your force is pretty much zero. You're not accelerating, you're just continuing.
Yeah, that's exactly right. When you're pushing off the table, all you're doing is getting yourself up to speed. Once you're up to that speed, Newton's first law comes into play. An object in motion will naturally stay in motion without any other forces acting. So once I get myself up to speed by pushing off that table, when I let go of that table, I don't need any extra force to keep me going. Newton's first law is going to keep me going. If I'm already in motion as a result of that push, I don't need any extra forces or extra pushes to keep me in motion. An object in motion naturally stays in motion unless you've got an outside force acting. And of course, realistically, there's friction acting in that case. So you would have friction. And I want to point this out because this is very counterintuitive. If I'm moving to the right, you're tempted to think there's got to be a force to the right. But not only is there not a force to the right, the only force that you have is one going left. Exactly. So you have to make sure you make this connection between forces and Newton's first law. Simply because you're moving in a certain direction doesn't mean there has to be a force in that direction. Chances are you've at least got one force going the opposite way. Sometimes that's the only one. Now, if I'm talking about what was going on while I was pushing off the table, while I was in the act of pushing, then yeah, that applied force would be there. And that applied force would be larger than the friction because I'm speeding up. So yeah, that's what it would look like while I'm doing the pushing. If I had one of you guys pulling me to get me up to speed, you got it. It'd be the same thing, just with tension force there. Questions so far? Don't you just love force already? Okay.
Wait, how would you do like for friction of like a wheel? Would it be kind of like circular?
The friction that you get due to wheels has to do with the bearings inside the wheel, or it could have to do with how not perfect the wheel shape is. So it's kind of tricky. Basically, in terms of friction, we always just point it in the opposite direction. But usually, if you want to get down to the nuts and bolts of it, the friction with wheels is due either to bearings or the imperfect shape of the wheel.
I'm not saying like how would you show that? Would you try to put a like opposite force that's kind of like a kind of circular arrow? Or
You mean when you're talking about what's going on the inside there? Yeah, I mean, within a wheel, you've usually got a lot of tiny little bearings that go around a part that make it spin in the middle there. So the friction caused on each of these, I guess, would be pointing in different directions. But all of those directions would be the opposite direction the wheel's going. So yeah, it would always be pointing the opposite direction of the spin. It's resisting that motion. Does that answer your question? Kinda. That's the idea, though. Were you asking something different?
kind of more just like assuming it's just like a rod that's in like a bushing or something, where there are no bearings, it would just be kind of like would you actually have the arrow be curved?
No, it would always be going straight in the opposite direction of the motion. Because when it's going like that, the resistance to the movement is always going to be backwards, regardless of how strange your wheel or other object might look. So, in terms of other scenarios, let's say that we just got rid of everything. We got rid of the skateboard. We also get rid of the floor. I am now in free fall. It would just be gravity. So if I'm in free fall, I have been skydiving, by the way. Awesome experience. If I am in free fall, gravity is the only thing acting. But of course, realistically, there is a little bit of force going the opposite direction. Yeah, air resistance. And the way that we label friction is with this little guy. So this is the Greek letter mu. We use it for coefficients of friction. So I also put it next to the F. So this means force of friction. And you can use that whether you're talking about air resistance or whether you're talking about friction on a level surface. That applies for any of those. But yeah, when something's in free fall, you've only got gravity acting. Because generally when that happens, they say ignore friction. Because air resistance doesn't really come into play until you're moving fast enough that that air actually would affect it. And that takes a while. So I also want to point out a couple things about Newton's other laws. That's kind of Newton's first law there. Newton's second law is basically an equation. And that equation is this. Force is equal to mass times acceleration. In order to summarize this, it basically says where you've got a force, you've got an acceleration. If you're putting a constant force on an object, it's going to be speeding up or slowing down, depending. Because if you've got a constant force of friction on an object, it's slowing down. And you can kind of see that just by this little air cart here. Right now, there are no forces acting, and that's why it's holding still. An object at rest naturally just wants to stay at rest. But if all of a sudden I put a force on it, it's going to start moving and pick up speed. And it picks up speed pretty good. Whoa. Still works. So again, when you've got a constant force, you've got a constant acceleration. It's going to be picking up speed. It's going to be going faster and faster and faster and faster. If there was no air resistance, and if there was no ground friction, that fan cart would pick up speed forever. It would continue to go faster and faster and faster. Now, realistically, you've got air resistance, and you've got ground friction. So eventually those would equal out, and there'd be a point where it's not going to go any faster. Just like when you skydive, there's a point at which you're not going to be speeding up anymore. Your terminal velocity, they call it. So, but other than that, yes?
Yesterday I was really bored at like 11:30 at night. I was on YouTube, and I recommended it was golf ball reaches terminal velocity. That's these guys who have the air pressure.
Yeah, the air pressure, and he holds it.
And he holds it and like funnels all the air, and the golf ball turns so fast that it breaks like terminal velocity.
Well, that's interesting.
You should look it up.
I should look it up.
That sounds really cool.
Nice.
Really cool.
Yeah, a lot of interesting things happen at terminal velocity. But yeah, that's Newton's second law. An object in motion naturally stays in motion unless another force acts on it, and that force that would act on it is described right here. Newton's second law. If you have that force, you're going to have an acceleration. And if you have an acceleration, you can bet that there's a force acting. All right. So that's Newton's second law. Newton's third law, you've probably heard recited, and you probably almost know it by heart by now. Who can recite Newton's third law or get close to it? Good guess, but no. That's Newton's first law. Yes?
All actions have an equal and opposite reaction.
Exactly. For every action, there's an equal and opposite reaction. That's Newton's third law. But I really, in this class, it's not so much about me wanting you guys to memorize things. It's about me wanting you to understand how the world works. So whether or not you can memorize Newton's third law, I really could care less about. I'd rather it be you know what it actually means and how it all works, rather than being able to, recite the thing. So I'm just going to quick summarize what Newton's third law says right now. Let's say I'm putting my massive muscles, 100 newtons of force on this table. Guess how many newtons it's putting on me? 100 newtons. Exactly. What do you suppose if I put 1,000 newtons of force on it, and I'm pushing so hard that it jars free from the ground and flies out the door? How many newtons of force is it putting on me if I'm putting 1,000 newtons on it? 1,000. Regardless of what's happening with motion, whether it's holding still or whether it's moving, the force that I put on it will be the exact same as the force that it puts back on me. And that's always the case when you've got two separate objects. Newton's third law is always about two objects that are interacting, those two forces. We would say the force of the table on Mr. Hathaway is equal to the force of Mr. Hathaway on the table. And you could say that for a zillion different things. The force of the apple on the wall is equal to the force of the wall on the apple, regardless of whether it goes through or not. If I threw this through the glass window in the door and it busted right through it, while it's contacting the glass, the force of the glass on the apple is equal to the force of the apple on the glass. Always.
Glass go through the apple.
Well, it comes down to there being more than that force involved, because I've imparted a force to it, and, we get into more of those forces later on in the chapter. For right now, this is sufficient for our understanding. But hang on for that. So, those are Newton's 3 laws. And now is your test. Let's say we have this apple, and I toss this apple in the air. I would like you to consider 3 positions. Right when the apple leaves my hand, and it's moving up very quickly, the position where it's halfway up, and the position where it's at its apex. I would like you to think about what forces are acting on the apple at those points. So here's the apple right after it leaves my hand. Maybe it's an inch off my hand right now. What forces are acting on the apple at this point? And we'll say you can ignore air resistance here.
Gravity.
Okay.
The applied.
No, it's not applied because it's already left.
Okay.
Yeah, it's left.
So do we have an applied force?
No.
Okay. So what else we have?
We don't have normal because there's nothing under it.
Oh, is this it?
Yeah. There has to be something going up.
Wouldn't there be for air resistance?
I just said you can ignore air resistance. Otherwise, there would be. Yep.
Well, okay, so you're going this way up, and it still has potential energy going up this way.
Right.
So what else would be there?
Well, sounds like we're kind of struggling with this one. So let's just move on to the second one. Maybe we can come back to this. So now we'll call this position 1, right when it leaves the hand. Position 2, now it's halfway up to the point where it's going to turn around and come back down. So what forces are acting here?
Gravity.
Okay, gravity.
Wouldn't it be the same as when it just left?
It might be. I don't
I
know.
mean, there might be less of.
It is still moving up, though, here.
Yeah. So it's the same as the first one. We don't know.
Okay. How about when it reaches the top? Okay, we've got gravity. Anything else?
Yeah. Gravity.
Gravity, man.
So you're saying this is the same for all 3 scenarios, even though we're going very fast, slowing down a little bit, and now we're basically stopped in the air because we're in the process of turning around.
Yeah.
Other opinions on this? I know what this side of the room is thinking. What do you guys think?
Yeah, it shouldn't be.
I feel like there's a neutral force on the third one.
What direction would that be going?
Down.
So maybe there's another force going down.
I mean, yeah, that makes sense. 'Cause- wait, what would the neutral force be? It's like the momentum.
Okay.
But isn't that just part of gravity?
Anybody want to say anything about an upwards force anywhere here?
That's what I was
Because it is
saying.
moving up after all.
Yeah,
No, it's already.
that's what I was saying
then
though. But
it's just the velocity that's being changed by the force going down is pulling the velocity down. Because the velocity is going up in one direction, but now it's starting to pull down, and once it reaches the third one, velocity is 0,
Sure.
and then it's going to start to accelerate downwards.
Okay. Good explanation. Yes.
Wouldn't there be an applied force on the first 2 because you're throwing it upwards?
that's what I said.
No,
Gavin
buddy,
said
no.
it already left his hand.
No,
you said once it leaves.
Yeah,
his
once it
hand.
leaves, like the skateboard thing. Once he
Said
pushed
the
off,
skateboard
you
thing.
start.
How would it be going upwards?
Yeah, but
How would he
once
be
push
moving?
off, then applied force is no more. Yeah.
Yeah.
once that contact is gone,
I realize that.
it shouldn't be a thing.
But once you-
Something has to be pulling outward, so what would it be?
The prior applied force.
Yeah.
And we can't talk about that because it's not touching his hand. Well, it's still there, so I guess yeah,
So-
you could still say applied force because it's still going up. The force is still carrying the question.
Mhm.
Right?
Now, there's a reason that I brought up this question. And the reason is because I actually did, for my master's degree, a study on this exact thing. Where did my... I just had it out.
Like talking about like where there's nothing fully touching it, but the prior energy from the force is there.
Yeah.
Is it energy or is it just...
Well, I'll get it out if I can find it. I showed last hour. The master's thesis I wrote to get my master's degree, I compared student misconceptions in physics with past defunct scientific philosophies. And what that means is basically, I found that students that come into physics class most often have a wrong way of looking at force, but that wrong way is right in line with historically the way scientists have looked at these things on force and motion. So those of you who said there is no applied force, you guys are actually right on the money. That's the correct Newtonian way of looking at this. But if you were tempted in the least to say that there was an applied force left over from the hand, and maybe here it's a little bit less because it's slowed down more at this point, this is the Galilean way of looking at things. And so it's not like, these ideas are just coming out of nowhere. If you thought this, you're thinking the exact way Galileo thought before Newton. And so there's nothing wrong with that at all. But the hard thing about this chapter, and the thing I'm going to be harping on over and over and over again, is that as soon as you let go of an object, there is no force whatsoever left on it. And as you guys were saying before, the reason it slows down is because there's gravity here, and the reason it's continuing to go up is because that force, there was an applied force. I did throw it up originally, and then Newton's first law took over. An object in motion naturally stays in motion, like this apple did, until an opposite force was acting, and that force was gravity, which is why it was slowing down. So good job with that. Good job with that. Last hour, everybody said there was an applied force. So you guys are well on your way to becoming Newtonian thinkers. Well done. I'm just going to go ahead and hand out the first worksheet. It's not